I'm Dr. Kashif Sabi, Associate Professor in the Department of Physics, Qaid-e-Azam University, Islamabad. I'm a theoretical condensed matter physicist, and my current area of interest in research are electron transport and collective excitations in low-dimensional systems, such as graphene. And graphene is the topic of today's talk. The title of the talk is Graphene, a Revolutionary Material. An outline of the talk is given on this slide. The first question that I'm going to address is, why are we interested in studying and developing new materials? After that, I will give an introduction to graphene. That will be followed by electronic properties of graphene. And then I will discuss why is there so much interest in graphene today. And I'll finally end this talk by a discussion of the present status and future of graphene research. The first question, which is very important, is why do we study and develop new materials? There are two aspects of it. The first one is the fundamental aspect. New materials usually exhibit novel, new phenomena, usually due to their interactive behavior. Due to the charge carriers interacting with each other, we find new types of collective behavior, new types of quasi-particles, and new types of order. A case in point are the quantum Hall systems, which were realized in semiconductor heterostructure, where the quasi-particles are anyons, which are very different in their properties from fermions and bosons. Another aspect, which is also very important in the study of new materials and their development, is the practical aspect. New devices based on these new materials usually have a huge impact on our lives. And a classic example of that is the transistor. Transistor in many ways is considered to be the most important invention of the 20th century. And here on this slide, we see the picture of the three inventors of the transistor. These are Bardeen, Shockley, and Brattain. And on the right is the original point contact transistor, which was invented in AT&T Bell Laboratories. Transistor is the fundamental building block of modern electronic devices. And as we look around us and in our lives, what we see is that these new devices have actually changed the very way we live our lives. And without the transistor, it would not have been possible. So, in terms of practical aspects, study of new materials and building devices based on those new materials is very, very important and does have a huge impact on our lives. The long-term trend in computer hardware follows what is known as the Moore's law. The number of transistors on a chip doubles approximately every 2 years. Since the invention of the integrated circuit or the silicon chip, this trend has been followed for the last almost 50 years. But we are coming to a time where it doesn't seem possible that this trend would continue. And so the search for new materials or devising new methods of creating new devices is becoming ever more important and pressing. So that is another incentive for developing new materials, and a very important one. Now, in terms of an important new material which has taken the world by storm, scientific world at least, is graphene. And now we will come to graphene and discuss some of its important properties. Graphene is made up of carbon atoms. Carbon is an old material with various new forms. The older forms are graphite and diamond. We are very familiar with them. But several new forms have been recently discovered, such as buckyballs, carbon nanotubes, and graphene. And all these newer forms have this special feature that they are low dimensional. Graphene is also called the mother of all graphites, because if you stack graphene layers, what you obtain is graphite. So these stacked layers of graphene is graphite. If you roll the graphene sheet into a cylinder, what you obtain is a carbon nanotube. And graphene sheet in the form of a ball is a carbon buckyball. So all of these different structures, in one way or the other, are based on graphene. So graphene, by definition, is a single layer of graphite. It's a unique two-dimensional electronic material. It has structural rigidity, which is due to strong in-planar bonds, and its electrical conductivity is due to the pi electrons. I'll come to these two features very soon. So what was the conventional wisdom till 2004 regarding graphene? So what was the conventional wisdom till 2004 regarding isolation of graphene? The conventional wisdom was that a graphene sheet would not be stable against thermal and other fluctuations. So whenever you have a graphene sheet in nature, it would eventually turn into either carbon nanotubes or buckyballs, or you would find them a graphene sheet and stacked up layers in graphite. But a freestanding graphene sheet would not exist in nature. So if it was impossible to find graphene in isolation, it would be impossible to do systematic study of its physical properties. So that was the conventional belief till 2004. But that conventional belief was overturned in 2004. But that conventional wisdom was overturned in 2004. And that was primarily due to the work of Andre Geim and Kostya Novoselav at the University of Manchester. Before them, others were also doing work on isolation of graphene. Important work in this direction was carried out by Walter de Heer at Georgia Tech and Philip Kim at Columbia University. Philip Kim's group, what they had been doing was they would attach a graphite sample to the cantilever of an atomic force microscope, AFM, and would drag it along on a substrate, and flakes of graphene would come off. But they weren't able to get a single layer. They would have usually 10 to 15 layers. But Geim and Novoselav found an ingenious and sort of a very simple method of obtaining a single layer of graphene. What they did was they attached a Scotch tape to graphite and peeled it off. A few layers of graphene would stick to the tape, then they would attach another tape to that, and by systematically peeling off, they would bring it down to a single layer which they could deposit on a substrate. And by optical microscopy, looking at it under an optical microscope, they were able to identify that a single layer had been deposited. So Philip Kim, in many of his public lectures, made the comment that we were scooped by a piece of Scotch tape. A very simple method, but that eventually led to isolation of a single layer of graphite, that is graphene. So in layman's terms, this is called the Scotch tape method. In technical terms, it's called mechanical exfoliation. And so mechanical exfoliation followed by optical detection led to the isolation of a single layer of graphene. Nowadays, there are other preferable fabrication techniques, such as epitaxial growth of graphene, thermal decomposition of silicon carbide, chemical vapor deposition of hydrocarbons on metal surfaces, which are then etched away. Gaim and Novoselov, they not only isolated a single layer of graphene, but they were also able to do systematic studies of their electronic properties. This combined work was very important and led to their getting the Nobel Prize in Physics in 2010. In their classic paper that was published in Science, they were able to show that by tuning the gate voltage, they could have electron transport. This is the region where the electrons are contributing to transport, to conductivity, whereas by tuning the gate voltage, they could go into the hole region, where the holes are the charge carriers, and they are contributing to the conductivity. And conductivity was shown to be linearly related to the gate voltage, and gate voltage could be used and can be used to tune the charge carrier density. So in a single system, they were able to obtain electron and hole transport. So both electron and hole transport regions could be accessed by changing the gate voltage.